Hello students, welcome back to JCE Connect series of lectures. So we have already started module number 5, that is design of beams. So in previous lecture we have discussed about the introduction of beams, types of beams, then lateral stability of beams, factors affecting lateral stability of beams. So those all things we have been discussed in the previous lecture. So in this particular lectures I am going to discuss about behavior of beams in a bending, then the plastic hinge, how the plastic hinge forms, and what are the advantages of forming a plastic hinge, then the factors affecting plastic moment capacity. So these three things I'll be discussing in this particular lecture. So before discussing the behavior about beams in bending, so let us uh, study about plastic theory of beams. That is a basis of plastic theory. So this plastic, what the plastic theory says, so it is related to the steel. Since we are studying the steel structures, so we have to study about the steel only. The structural steel is characterized by its capacity to withstand considerable deformation beyond first yield. Without the fracture, during the process of yielding, the steel deforms under a constant and uniform stress known as yield stress. This property of steel is known as ductility and is utilized in the plastic design methods. So as we know, the stress strain behavior of a mild steel when it is being tested in a UTM, so we get the deformation as well as the behavior of that material under tension. So and also uh, the behavior of ductile material as well as the brittle materials. Since the mild steel behaves as a ductile material, so we get a large deformation before its failure. So as we know, in elastic design method, a structure is allowed to take up a load up to a certain limit well below the yield point, and usually extreme fibers are allowed to reach a yield stress, and the remaining portion will have a stress lesser than the yield stress. So this is in a uh, elastic zone what we get this points, and therefore we will not be using the full capacity of the steel. In such case, that is in elastic theory, we are not at all using the full capacity of the steel. Since steel is a ductile in nature, it will be capable of taking a huge amount of deflections or the deformations even after crossing the elastic limit without any failure. But what happens in the plastic zone? So due to the property of ductility or the ductile nature of steel, steel possesses a reserved strength beyond the yield strength. The method using this reserved strength is called plastic method of design. So that is, in plastic method we are using this extra load carrying capacity or carrying ability of a steel. Here we are using ultimate load for the design purpose. Therefore, this method is also known as load factor or ultimate load design. So this method leads to economy in design, and in plastic analysis we use idealized stress strain curve. And it may be noted that large amount of plastic deformation is useful for the section to develop a plastic hinge. So how the plastic hinge forms, so what is the nature of plastic hinge, we'll discuss next. The plastic design is an aspect of the limit state design that extends the structural usefulness up to the plastic strength or ultimate load carrying capacity. I'll repeat, the plastic design is an aspect of the limit state design that extends the structural usefulness up to the plastic strength or ultimate load carrying capacity. So that is, in plastic method we are using the extra load carrying ability of a steel, and even because of the ductile nature of the steel, it is capable of taking a huge amount of deformation even after crossing the elastic limit without any failure. So that is the advantage of having a plastic section in a structures. So here this uh, curve or this stress strain curve represents the ductile nature of the steel. So we have studied this type of a curve in a basic material testing lab when the mild steel is being tested in a UTM under tensile loading. So we get the yield stress, then we get the ultimate stress, then the fracture, how the yielding takes place. These all things we get about the mild steel. But in uh, plastic theory, this curve is being idealized, that is, a simplified stress strain curve is used in plastic design theory of structures which neglect the strain hardening of members shown in figure. Means one can assume this uh, curve, this one. So whatever the curve you are having, this type of a curve, one can neglect the strain hardening portion and only can take the linear elastic zone and the linear plastic zone. This is the idealized stress strain curve in a plastic theory. So this type of curve will be directly taking and studying the behavior of the members in a steel structure. That is, given a simplified stress strain curve is used in a plastic design theory of structures which is neglect the strain hardening of the members, and that neglected part which is being represented by like this. Next, then the stages of bending of a beam, how the uh, beam start bending, and what are the what are the nature of the bending of the beam, what are the how the stress is generated in the beam. Those all things we'll discuss now here. So if we start or consider a simply supported beam subjected to an increasing load, and as we know a beam is a horizontal member and it is being subjecting always a load in a vertical direction that is perpendicular to the longitudinal axis, and because of the load a beam starts bending. Hence a bending is nothing but a state of stress. Because of the load, the stresses are induced in the beam, hence the beam starts bending, and those stress variations we can draw. And here we are considering a simply supported beam subjected to an incremental load. When that uh, when the beam is been subjecting to the loading, so the upper part of the beam is subjected to compression and the lower part of the beam is subjected to tension. That is, upper part of the beam fibers are subjecting to the compression, they get contracted, and the lower part of the beam fibers are subjecting to tension, they get elongated. Okay, so this is the nature of stress induced in the beam. And if we consider a simply supported beam, and when it is been subjecting to incremental load at the mid span, it is shown here, then when the load is being increasing gradually, so what happens, at first the stresses at the extreme top and bottom fibers will be less than the yield stress. So we have seen the stress strain curve of the steel so previously, and we know what is the yield stress and where it takes place. So when it is been applying to this beam, and the beam is been subjecting to incremental loading at the mid span, and when this load is been increasing gradually, at first the stresses at the extreme top and bottom fibers will be less than the yield stress. Then what we get, so we get the beam remains straight when the load is being unloaded. If you load it and unload it, again we get back to its original shape and size. So that is the elastic nature of, that shows the elastic nature of the beam. That's why I said at first the stresses at the extreme top and bottom fibers will be less than the yield stress. That is, so this is the stress diagram what we get in a first stage. This is the first stage when the load is at a lighter in a lighter part, just the load is been applied and the removed. So it shows the elastic nature of the beam. That means the beam remains straight when unloaded, and the stresses are within the elastic limit, or we can say the stresses are well below the yield stress. So that is F, or you can say the sigma is a stress induced in the upper part of the beam as well as the lower part of the beam. The upper part of the beam or beam is been subjecting to compressive stress, and the lower part of the beam is been subjecting to tensile stress. That is, if you take here, this upper part is subjecting to compression and the lower part is subjecting to tensile. So this upper part induces a compressive stress and the lower part induces tensile stress. So this is at the first stage when the load is been applied and removed, then the beam remains straight when unloaded, and the stresses in beam will be well below the yield stress. Then as the time passes, then if the load is been increasing gradually and at a particular instant, again I'm taking the next case, further if you increase the load at gradually at a particular instant, both compressive stresses as well as the tensile stresses will become equal to the yield stress. Means this is the stress strain curve what we get next. So next, so in the second stage, when we keep on increasing the load gradually, what happens here, the beam remains straight when unloaded, remains straight, but the upper and the lower part of the beam are reached yield stress. So that is, as I say, as the time passes, if the load W, if it is increasing gradually and at a particular instant of time, both compressive stresses as well as the tensile stresses. So as I said, the compressive stresses, here we get the compressive stresses, that is FC, and here we get FT, that is compressive stresses, and the tensile stresses will become equal to, that is yield stress as sigma y, or you can say it as a Fy. at, at this stage, the moment carried by the beam is known as yield moment, and that yield moment is given by, that is, my is a yield moment is equal to Fy into ZE. We can give Fy into ZE at this stage. The moment, if you want to calculate the moment at this stage, when the upper fibers and the lower fiber, that is compression zone and the low tensile zone, just reached the yield point, then at this stage whatever the moment you get, that is the yield moment, or it is called the elastic moment, and this elastic moment is given by Fy into ZE, where Fy is called as yield stress and ZE is the elastic section modulus. I hope you understood this one. So Fy is called as a that is a yield stress, and ZE is called as a elastic section modulus. Then the further, sorry, so again further, if we increase the load, further you increase the load in the third stage. I'm talking about third stage. The first stage, just we have loaded and unloaded it and the stresses were well below the yield stress. The second stage, we are again further we have loaded and we have reached the yield stress both in the upper part and the lower part of the beam. And the second stage, the yield moment we have obtained as Fy into ZE. And then the third stage, further if we increase the load beyond the yield, so when we increase the load, and what happens here, the yield gets penetrated into the inner fibers. So here what happens, the beam remains slightly bent when unloaded, means we have crossed the yield point and we are keep on loading. So because of the yielding, the beam remains slightly bent when unloaded, and because of this what happens, the yield gets penetrated, so that you can see here in this figure. So you can see here the yield get, sorry, in this figure we can see here this part. I'm marking here this part. Let us call this part as a E. Here also this part. Okay, so here what happens, the yield gets penetrated into the inner fibers, and for a depth E, here I mark depth E, because this in the third stage we are loading beyond the yield point. When it is been loading beyond the yield point, so what happens, because of the yielding of the fibers at the compression zone as well as the tensile zone, the beam remains slightly bent, and when it is been unloaded, so because of that what happens, the yield gets penetrated into the inner fibers for a depth E, and called the depth of penetration. This E is called as depth of penetration, which is been shown in a figure number 3, that is in a stage number 3. And at this stage, the moment is known as elastoplastic moment. So I'm repeating, in third stage the moment is known as elastoplastic moment. In the second stage, the moment we called as a elastic moment, because all the fibers still they were in elastic zone. So once they crossed the elastic zone and they are entered in a plastic zone, the part of the fibers become elastic and still the part of the fibers became plastic. Hence the third stage is called as elastoplastic stage, and the moment is known as elastoplastic moment. Here some portion will be under plastic range and the remaining will be under elastic range near the neutral axis. So if we further increase the load, again after third stage, what happens? If we further increase the load, see again, take it the fourth stage. If we further increase the load, what happens? The yield will penetrate further. I'll show you this picture. So here the plastic hinge will get formed. In the fourth stage, the plastic hinge will form. Then this is the stresses induced in the beam. So if we further increase the load in stage number 4, the yield will penetrate further. I'll show you the yield will penetrate further. So see here, just look at this portion as well as this portion. So this is the section plastified neutral axis. The yield will penetrate further towards the neutral axis from both the sides. From both the sides means from compression side as well as from the tension side. So both the side the yield will get penetrate towards the neutral axis. And a time will reach when all the fibers will be subjected to yield stress. See, look at here. This all the fibers are being subjecting to yield stress. So all the fibers have got yielded. The third stage, what had happened? Only few fibers have got yielded, and the remaining fibers were in elastic. So means it was in elastic condition. Means they are still able to take the load. But when we have increased the load further after third stage, all the fibers have got yielded and the yield has got penetrated from both the side, that is from the tension zone as well as from the compression zone towards the neutral axis. All the fibers have got yielded. And the time, as I said, the time has reached when all the fibers will be subjecting to yield stress, that has shown in this figure number 4. And the moment carried by the beam at this stage, the moment carried by the beam at this stage is known as plastic moment, that is MP. That is MP. In the third stage, first and second stage, we have called the moment carried by the beam as elastic moment. The third stage, we have called the moment carried by the beam as elastoplastic moment. And in the fourth stage, we are calling the moment carried by the beam as plastic moment. And at this stage, the moment is been calculating, that is MP equal to Fy into Zp. Fy is the yield stress, where Zp is plastic section modulus. So we calculate MP equal to, that is Fy into Zp. We calculate Fy into Zp. And the neutral axis of fully plastic section passes through the equal area axis. So suppose this is the neutral axis we are having earlier. Where is this one? So see, this is the neutral axis before getting the plastified neutral axis. This was the neutral axis we are getting, and as the load was gone increasing and the neutral axis gone shifting, then the axis we get as like this. This one neutral axis we get. So here we get the plastified neutral axis. This is called as a plastified neutral axis, and this is neutral axis, and this one is equal area axis, that is plastified axis. This is called as equal area axis. Okay, if the beam section is taken symmetrical section, if suppose this is a symmetrical section, for a symmetrical section, if it is symmetric about both the axes x and y, then the neutral axis and the plastified axis will be both same. Neutral axis is been calling as a plastified axis. Okay, if the section is unsymmetrical, then that neutral axis get shifted based on the forces of compression and tension. Okay, so the neutral axis of a fully plastic section passes through the equal area axis, then further, and beam section in this stage, that is stage number 4, has reached its maximum resisting capacity. So here in the stage number 4, in this stage, if you take this stage, what happens here, the beam section in this stage has reached its maximum resisting capacity, and any further increase in the bending moment, if you increase the bending moment further or loading, cannot be resisted by the section, and an instability is reached. At this stage, an instability will reached, as would happen if a hinge was provided at the section. Then a plastic hinge will be forming here at this point. If you take this point, a plastic hinge will be forming here, marking here. So at this particular, because all the fibers have got yielded, because further if you increase the load, it won't be taking, just simply it rotates both the parts. So here you get like this, here the hinge will be forming, simply it rotates. That is what we call as an instability is reached, as would happen if a hinge was provided at the section, that is a plastic hinge has formed. This is called a plastic hinge formation. A plastic hinge was formed at this section. A plastic hinge is sometimes also called as a rusty hinge. You might have heard in when you open the doors, if you not open the doors for a long time, so just if you open the doors, how that hinge will resist the moment. Likewise, this plastic hinge uh, will resist the moment, and that plastic hinge somewhat also called as rusty hinge or a friction hinge. And at this stage, area of the compression zone, if you take the area of a compression zone or the tension zone of the section, are equal to half of the area. This area as well as this area, if you take, so these areas are equally divided, a by 2. If this is a by 2 and this is also a by 2, and total compressive force on this section is equal to the total tensile force on this section. This means that the neutral axis at this stage, called the plastic neutral axis, divides the beam section into two equal areas. Hence, whatever the axis forms, that axis is called as equal area axis. And the moment of resistance of this section at this stage is called as plastic moment of resistance, that is MP, or the plastic moment. So this is about the bending of the beams stage wise. I explained here. So in the first stage, just we put the load and unload it at lighter side, then all the stresses will be well within the yield stress. The second stage, when we further increase the load, the stresses will reach the yield stress, and at this the stage, the moment is called as a yield moment, and that moment is been calculating, that is F into ZE. ZE is the elastic section modulus, and in the third stage, part of the fibers get yielded and they get penetrated towards the neutral axis, that is called depth of penetration, and at this stage whatever the moment we get, we call that moment as a elastoplastic moment. And further, if you increase the load, the third and the fourth stage, all the fibers yielded and they penetrating towards the neutral axis from both the sides, that is from compression side as well as from the tension side, and axis will be forming, and that axis is called as a plastified neutral axis. And about that plastified neutral axis, the section starts rotating, and whatever the zone created, that is the point, like this point is called as a plasti plastic zone, and this zone is called plastic zone, and this particular point a plastic hinge will be forming, and this hinge is also called as a rusty hinge or the friction hinge. I hope you understood the stages of bending for the beam. So based on this, in steel structures, the classification of sections are being made. That is very very important for solving the beam problems. So why I would explain this concept is, so whatever the classification of sections you make for this, for solving of the beams or in a design of a beams, the classifications are like plastic sections, that is class 1, or the compact sections, semi-compact sections, or the slender sections. There are 4 classifications of sections which are given in ISA 800 2007, and those classifications are being made based on this bending of a beam. If you understand this concept of forming a plastic hinge or the plastic section, or partially plastic or the slender, you can easily understand what are plastic sections, what are compact sections, what are semi-compact sections, what are slender sections. And once you know which sections are plastic sections, which sections are semi-compact sections or the compact sections, which can be used in the steel structures depending upon their use. So this is very very important concept, and try to understand this concepts stage wise, and you will understand in better way what are the plastic sections. I hope you understood this concept. Okay, next. So this is the stress with increasing bending moment at a center of span. Then what is a plastic hinge? So this is very very important. After studying that stage wise bending of a beam, so what do you mean by plastic hinge? So again, we have taken a simply supported beam subjected to central loading, and the stage wise how it has deformed is been clearly you can visualize here. So it is completely shown here which is the plastic zone and which is the elastic zone and the elastoplastic zone, then the plastic zone. So we have considered a rectangular cross section of width B and a depth H, and this beam is been subjecting to central loading. So that is, consider a simply supported beam under a concentrated load P at the center. As the load increased gradually, the mid-span section develops a stress, that is Fy. As the load is further increased, the yield stress penetrates deeper at a moment, that is plastic moment. As I explained earlier how that plastic moment and all develops. So here, as the load is further increased, the yield stress penetrates deeper, and at a moment MP, a plastic section is developed at the center. Then plastic section developed at the center, then the formation of hinge under the load, that is under the point load, constitute a mechanism of failure. So because of the formation of plastic hinge, because of the formation of plastic hinge, so here look at this figure here, here the plastic hinge has formed, and this zone is plastic zone. So completely all the fibers have got yielded from both the side. if you take this as the central axis from both the side, from the compression as well as from the tension zone, all the fibers have got yielded, and at this particular point a hinge has formed because of the yield. And what happens because of the hinge formation, that is a plastic hinge is a zone of yielding due to flexure in a structural member in which a rotation can take place at a constant restraining moment mp of the section. Here the rotation will take place at a constant moment, and that moment is called as plastic moment. So this is how the stage by stage, the plastic hinge has formed. At initial stage, when we are loaded, the load was lesser than the yield load. Then we have got the deformation. Then when it has reached the yield load, again we have got the second deformation, and the third deformation. This was the third deformation. I can show here. This was a third deformation, final deformation, when that load has crossed the yield and reached the plastic load, and at that load completely it forms a plastic hinge, and the member in which the rotation can take place at a constant restraining moment and develops a plastic moment. So this is about the plastic hinge formation. Again, what do you mean by plastic hinge? A plastic hinge is a zone of yielding due to flexure. I can say a zone of yielding at this point. A zone of yielding. So this particular point, a zone of yielding due to flexure in a structural member. Actually, hinges do not form. It can be seen that a large change of slope occurs. See, you can see a large change of slope is been occurring here. You can see from this side as well as this side. I'll show you a large slope is occurring like this. A large slope is uh, occurring in a smaller length of the member at a position of maximum moment. Then a structure can support the computed ultimate load due to the formation of plastic hinges at a certain critical sections. Then the member remain elastic until the moment reaches the value of plastic moment. So any additional moment will cause the beam to rotate with a little increase in stress, and the rotation occurs at a constant moment, that is MP. Okay. Hence the plastic hinges are the first at the section subjected to greatest deformation or curvature. So this is about the plastic hinge formation, how the plastic hinge will form, and this mm, classifies next the sections that I explained, that is a plastic, compact and semi-compact. So there you can easily understand, if you understand this concept, you can easily understand the classifications of sections. I hope you understood this one. So next. So what are the factors affecting plastic moment capacity? So the first is lateral buckling of compression flange. So what do you mean by lateral buckling of compression flange? So look at this figure. It has buckled laterally, and also it is been twisted. Here what happens? It is a characteristic feature of the lateral buckling is that the entire cross section rotates as a rigid disc. You can look at this figure. So here you can look at this one. The entire cross section rotates as a rigid disc without any cross sectional distortion. This phenomenon is known as lateral buckling. It buckled sideways. So this was the initial position when the load is been applied. So this has buckled sideways, and this buckling what we call as a lateral buckling. This is out of plane deflection. So in plane deflection we call as a bending, and out of plane deflection it has buckled. This is called as a lateral buckling, and it is accompanied with also torsion. So hence lateral buckling is or a torsional buckling of a beam. Suppose if lateral buckling takes place, then it has been given here. Sorry, see, in this one, if lateral buckling takes place, the beam fails well before it could attain its full moment capacity. So this is one of the reason, uh, that is which affects the plastic moment capacity. If suppose the beam has buckled before reaching the moment capacity, that is plastic moment capacity, then that is sorry the buckling can affect the plastic moment capacity. That is, if lateral buckling takes place, the beam fails well before it could attain its full moment capacity. The second, axial force. This is one another factor which affects the plastic moment capacity. As you know, this is the axial force has been shown, how the axial force will be acting in beams. So along its longitudinal axis, the axial force is acting along the longitudinal axis of the beam. So the effect of axial force is to reduce the plastic moment capacity of the beam. If suppose axial force is present, then it reduces the plastic moment capacity of the beam. However, as the beams are mainly subjected to the lateral forces, this effect may not be taken into account. So generally the beams are mainly subjecting to the lateral forces, hence the axial force is been neglecting, hence it may not affect much. If suppose present, definitely it affects the plastic moment capacity. Then third factor which affects the moment carrying capacity is local buckling of plates. Very very important. Before reaching the plastic moment, if the members buckle locally, definitely it affects the load carrying capacity of the member at ultimate. So this is the picture. You can see how the local buckling will takes place in the members. So here I have shown the local buckling in the top flange. The flange has got distorted because of the load applied. It has taken the sinusoidal, like a sinusoidal wave. So it has buckled. This type of failure, what you call as a local buckling. And you can see here also in this picture reveals that local buckling. So you can see the section AA is shown here, how the flange has buckled. Even the vertical member, that is a web, also has buckled at section BB is shown. This type of failure, what we call as a local buckling, and this local buckling will affect the load carrying capacity of the member, that is plastic moment capacity. So what happens, the cross section of the plate elements subjected to compression, that is a compression or a shear. So as I said earlier lecture, the flanges are being provided to take care of the moments, and web will take care of the shear. If the flanges are being subjecting to the moment in compression as well as in a tension, that is, when the plate elements are subjected to compression or a shear, may buckle before overall beam fails. Means before failing the overall beam, first they buckle by lateral buckling or yielding, and this phenomenon is called as local buckling. So which affects the moment carrying capacity. Then local buckling has the effect of reducing. Then if suppose local buckling takes place, it has the effect of reducing the overall load carrying capacity of the beam due to reduction in the stiffness of the member. So we need to prevent this type of a failure before failing of the overall beam. If suppose this type of failure is been taking place before reaching its ultimate load, then the beam or the element may become ineffective in carrying the load. So these are the three factors which affects the plastic moment capacity. So we can prevent this type of a failure, and we can provide the additional plates for the flange plates as well as for the web plates, which can reduce the failure of from the local buckling. If we reduce, definitely again this beam will fail by plastic. Then those sections, we can say it, they are as a plastic sections. We can make these sections as a plastic sections by strengthening the elements of the beam, that is flanges and web. I hope you understood these things what I have explained in this particular lecture. Please go through once again, try to understand this concept of bending as well as the formation of plastic hinge and the factors affecting the plastic moment capacity of the beam. This is very very important, and in my next lecture I will be starting section classification, which are generally used in the design of beams. And when we design the beams, there the sections are being classified as a plastic sections, compact sections, semi-compact sections, and slender sections. If you understand this concept and that concept, you can easily understand. I hope you understood this one. Thank you.